So today we're going to move beyond the dot product and the cross product and start to talk about some analytical geometry that will use the dot product and the cross product a little bit and build on some of the vector concepts that we've developed so far. So it's a two-part section, lines and planes. It's quite long. We'll split it into two lectures, and we'll start by talking about lines. Hopefully a familiar concept, and we'll be able to practice starting to apply vector ideas with something we're already quite familiar with. So the motivating question here is to recall Calculus 1 or even just pre-algebra, algebra 2, where we created lines using functions of x. Y is a function of x, and in particular we had the point slope form, y equals y naught plus m times x minus x naught, where y naught was the value of the line at x equals x naught, and m was the slope. So that gave you a line like this, and the question is now, how can we generalize this to three dimensions? Okay, so in particular, if you say z equals y naught plus m times x minus x naught, you haven't said anything about y, which means y could be anything, which means you don't have a line, you actually have a plane. You have one equation for three variables, which leaves you 2 degrees of freedom, which gives you a plane. And we'll get to that next lecture, but the question here is to say, how can we get something with 1 degree of freedom? We have three variables. In principle, we could say we need two equations, but that gets to be a little bit cumbersome to start thinking about that. So we're going to sort of go back to the drawing board and appeal to the concepts of vectors that we've developed so far this chapter. Okay, so here's the basic idea. What is a line? A line is a set of points that all are directed in the same direction away from some given point. So if you can give me some point in the line, then every other point in the line is a displacement away from that point, which points in either the same or opposite directions. So the key ingredients for a line are an initial point. We can call that r naught equals x naught, y naught, z naught, and a direction vector, which our book I think calls v, v1, v2, v3. All right, so say we've got our point r naught alone, there's our point. All right, now suppose you add 1v to that. You can use the rules of vector addition to say that you have gone this distance, and now you found a second point on the line. A third point could be obtained by adding 3v to that line, and that gets you this point in red. You could also add negative v, go the opposite direction, that gets you this point. Negative 2v gets you that point. So now suppose you want the points in between. You're basically adding different multiples of v, all right? 0v, 1v, 2v, negative 1v, negative 2v. And so what the theme here seems to be is that the line would be all possible multiples of v added to r naught. All right, not just discrete values, but the entire continuous set of real numbers are all possible points on this line. And so what we ultimately need is a parameter. We'll call that parameter t. If there's two lines, maybe we'll call the second one s. But t can be any number. T spans minus infinity to infinity, which traces out all possible multiples of r naught plus multiples of v. All right, and that will fill in all the points on this line in between the red dots. So this is called a parametric form of a line. You have some point in the line plus a parameter times a direction vector, and then that parameter has a domain, typically ranging from minus infinity to infinity, though it could be a finite domain if you were talking about a line segment. So if this seems new and crazy, you should know that it is not. It is, in fact, a perfect generalization of point slope form extended to 3D, and what you'll find often in this class is that what you knew how to do in the past is really just a special case of the more general things that we'll develop in this class. So let's go back to 2D, just for the sake of exploration, and look at a line in 2D. We have the point x naught, y naught, right here. And we have a direction vector, which we'll call a comma b. And this could be any multiple. In particular, it could be 1 comma m, where m is the slope, or any multiple of that vector. So if we were going to write this in our new fancy parametric vector form of a line, we would say, well, here's our point, and here's our direction here. And so we use the standard form, r equals r naught plus tb, and we can write that in vector form over here on the right. R is just the vector x comma y, the vector of coordinates. R naught is a particular set of coordinates, x naught, y naught, and v is the direction vector a comma b. So we get this right here. This gives us actually two equations, the top line and the second line. Here x equals x naught plus ta, y equals y naught plus tb. And what we can do here is we can take that first equation and we can solve for t. And if we do that, we get t equals x minus x naught over a. We can then take this value for t and plug it into the second equation, which gives us a new expression, y equals y naught plus b over a, x minus x naught. And b over a is just m. So this parametric or vector form of a line really, I'm getting a little ahead of myself, generalizes back, or it reduces back to point slope form if you drop from 3 dimensions down to 2 dimensions, and you do a little bit of algebra to eliminate this parameter t. Now we come to parametric form of a line. The vector form of a line is really just shorthand for 3 equations, which will be more familiar to you from Calculus 2, where you at least briefly were exposed to the idea of parametric equations. So we have our position, our point on the line, and we have our direction of the line, and this is our vector form of a line. But what that means is that x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. And this is sort of a standard parametric form of a line in 3 dimensions, parametric form. And you saw this in Calculus 2, and the image was to think that t is some parameter ranging from minus infinity to infinity, and as t changes, x, y, and z change, and you have some point in space. As t changes, you're tracing out some curve in space. This just happens to be a very specific curve, which is a straight line. So this is just a special kind of parametric function that happens to be a straight line. It's called parametric form of a line. And there's one other form of a line, which in my opinion is kind of silly. It eliminates the parameter t and gives you indeed 2 equations between 3 unknowns. If you take parametric form and you solve for t, you find that t is x minus x naught over a, t is also y minus y naught over b, and t is also z minus z naught over c. And so those 3 things are equal to each other. That is 2 equations among the 3 unknowns x, y, and z, which gives you 1 degree of freedom, which gives you a line. I suppose you could say that it is nice looking. It is indeed called symmetric form, and I do appreciate that it looks nice, but we won't use it much in this class. There'll just be a few problems in the textbook that will use this. We'll stick with vector form or parametric form in most of the rest of the class. Okay, so this would be a great place to sort of pause the video, review what we've said so far, write down any questions in the margins of your notes before you come to class about these general concepts. We're now going to move mostly to some examples. Okay, so first example, very basic example. Find a line through the 2 points, 1, 2, 3, and 4, 5, 6. Okay, almost, this is just plugging into a formula given at the beginning of the lecture for vector form of a line, except we're not given a point and a vector, we're given 2 points. All right, no big deal. How do we make a vector out of 2 points? We take the position of the second point, the head of the vector, and we subtract the coordinates of the first point, the tail of the vector, and that will give us a vector from the tail to the head. And so in this case, to create that vector, we do 456.2 minus 123.1. And we get the direction vector 333. So now we have a point and a direction. In fact, you could use either point. Doesn't really matter. You could create the line r equals 1, 2, 3 plus parameter here. I've used s times 333. Or you could create the line 456 plus t times the parameter 333. What you'll find is that these are in fact exactly the same line. These two sets of points are related by the simple relationship, I believe s equals t plus 1. And for any point on the first line, the value of s, if you subtract 1 and make that t, you'll get the same point on the second line. So it's the same line, it's just a slightly different parameterization. You may have heard in Calculus 2 that any curve in principle has an infinite number of parameterizations, and that's true here as well. These are just two slightly different parameterizations of the same line. Now, I think a lot of the rest of the examples relate to classifying the relationship between two lines. So given two lines, one relationship that those lines can have is that they are parallel. They point in the same direction. They're always the same distance apart forever. They go off into infinity, and they're always the same distance apart. So what makes two lines parallel? Quite simply, if they're pointing the same way. Slightly more precisely, we could say if their direction vectors are parallel, then the lines are parallel. We have exactly the tool we need to determine if two vectors are parallel. We just saw it, the cross product. So here's an example. Two vectors, two lines, R1, R2, and we have the two direction vectors 1, 2, -1, and -4, -8, 4. We simply calculate the cross product. ijk, 1, 2, -1, -4, -8, 4. We do the math. I'll briefly review this, although I won't certainly do it all the time. I components, we have I times 2 times 4. That's 8i minus -8 times -1 times I. That's, again, -8. So 8 minus 8 gives us 0. J components, j, -1, -4. 4j minus 4 times 1 times j, that's -4. K components, k, 1, -8, that's -8k, minus -4, 2k, that's +8k. And so all the components cancel, we get the 0 vector, the lines are parallel. Another thing that two lines could do is intersect. So this is a much more involved example. Given two lines, do they intersect? And if they intersect, where do they intersect? That last question in particular is of interest. Where do two lines intersect? So here's an example. We have two lines, R1, R2. They have different position vectors and different direction vectors. And it's definitely not clear, just looking at this, whether or not these two lines intersect. We have to do some math. So how do we go about thinking about this question? Here is the key concept for this kind of question, intersection questions. If two lines intersect, they share a point. There is some point in space where both lines exist. And so there is some value of these two parameters, s and t, that gives you the same point in space. Okay? So what we're going to do is we're going to try and set this equation and this equation equal to one another. And we do that component by component. At that point, the x values must be equal, the y values must be equal, and the z values must be equal. So we take the x components. Here we have, on the first line, 1 plus 3s. I'll write that here. In the second line, the x component is 2 plus 1t. And we make those equal to each other. Then we look at the y components. 2 plus 3s equals 7 minus t. And in the z components, 3 plus 3s equals 10 minus 2t. And if the lines intersect, all three of these equations must be satisfied at the same time. And you might notice that there are three equations here with only two parameters, s and t. So we're going to try and find values of s and t that satisfy these equations, but in general, you might not expect this to be true or satisfiable. And indeed, if you just pick two lines at random, you wouldn't expect them to intersect each other because space is awfully big and lines are pretty small. Nevertheless, these are textbook problems, and so you have a much greater chance of encountering lines that intersect if the problem says, do these lines intersect? So let's try and solve these equations. We can take this first pair of equations here that I've already highlighted, and we work that out, and we find that t is 3s minus 1. Then we take this second pair of equations, and we solve for t, and we get, in this case, t equals 5 minus 3s. So if these two equations are both true, then these two terms must be equal to each other. 3s minus 1 is 5 minus 3s. And when we work that out, we find that s must be 1. Now, moreover, if s is 1, that automatically tells us what t has to be because of these two relationships here. So if s is 1, then t has to be 2. So with these two equations, we have solved for the two parameters s and t. Now the problem is that there is a third equation. So here's kind of a warning. There's a third equation. We've already determined s and t, and there's an equation left. So we have to check and see if that third equation is also satisfied. Again, in the real world, in general, you would not expect this equation to be satisfied. But in the textbook, or perhaps in certain applications, you might expect that lines often intersect. And so we do this check. We plug in s equals 1, t equals 2, and we find that the equation is satisfied. So in this case, you can say we're maybe lucky that all three equations are satisfied with just two choices of parameters, s and t. And that means we've found an intersection. Now, where is the intersection point? We simply plug these two values of s and t back into the parametric forms of the equations up here. And we get, they should both give us the same point, and that's the point of intersection. So we plug those numbers in. We plug in s in the first equation. We plug in t equals 2 to the second equation. We get the point in each case is 4, 5, 6, and so 4, 5, 6 is the point of intersection. All right, so we talked about parallel lines. We talked about intersecting lines. Finally, if you have two lines and they're neither parallel nor intersecting, we call them skew. And this is the case that you ought to expect in general in the universe. So we follow the same process. We try and find an intersection point. And if we can't find an intersection point, then the lines are skew unless the lines are parallel. So we'll see how this works out. Actually, not in this video. But we showed how to look for parallel lines, and now we're going to show, we showed how to look for intersecting lines. If you find that it's not parallel and not intersecting, then it's skew. You should always check for parallel first because it's easy, in which case you don't have to check for skew or intersecting. So let's just work through this example. Do the following lines intersect? Same problem. So we write down the x coordinates, 1 plus 3t equals 2 plus s. For the y coordinates, 2 plus 2t equals 0 plus s. And for the z coordinates, 4 plus 3t is 1 plus 0s. Three equations and two unknowns. We take two of them. Here I'm going to choose the bottom two because they're perhaps tiny bit easier than the top one. I take the bottom two, and those two equations tell me first that t is minus 1, Then they tell me that s is 2 plus 2t. Well, that's 2 minus 2, which is 0, so s is 0. And so then I have to look at the third equation and see if t equals minus 1 and s equals 0 is a solution to the third equation. And I plug in t equals minus 1, I get negative 2 on the left. I plug in 2 plus 0, and I get 2 on the right, and those don't equal. All right, so there's no pair of parameters st that satisfies all three equations. That means the lines never occupy the same point, and therefore they do not intersect. We could go ahead and quickly do this. We could say, do the lines intersect? Or sorry, are the lines parallel? They definitely don't intersect. Are they parallel? And just by looking at them, you can sort of see that one is definitely not a multiple of the other. And so they're also not parallel. But suppose you didn't see that. Let's just quickly calculate the cross product of the two direction vectors. We have I, j, k, 3, 2, 3, and 1, 1, 0. We take the determinant. I components, 0, minus 3. J components, you can already see it's not 0, so it's not they're not parallel. J components, 3 minus 0. K components, 3 minus 2. Okay, and so the cross product is not 0. The lines are not parallel, nor do they intersect, and so they are skew. Okay, last example. This one's a bit harder. We now do a little bit, sort of 2 steps of geometrical analysis that makes our mathematics a little bit more challenging, but same basic ideas using vector form of a line. What is the closest distance between these two skew lines, R1 and R2? And so this really requires you to think a little bit and figure out a strategy for approaching this problem. And what turns out to be the key is that at the point of closest approach, the line of this line segment of closest approach between these two lines, you make a right angle with both of them. Okay? And you can see this because suppose you thought you were at the closest point and you were not at a right angle. Well, then you could shorten the line by sliding the point along so as to make the angle closer to right angle. That would be reducing the distance. And so it's when both angles are right angles that you are in fact closest between the lines, the closest distance. So we don't know what these 2 points are, these P1 and P2 points. But we know that wherever they are, the line segment P1, P2 is perpendicular to both V1 and V2. That might tempt you to take a cross product, and a cross product will certainly give you the direction of P1, P2, but it doesn't help you find the point of intersection. And so here it turns out what we need are to use 2 dot products. We have 2 parameters s and t that we ultimately need to determine to find P1 and P2, and so we need 2 equations, and we can simply look at these 2 right angles and say whatever P1, P2 is, it's perpendicular to V1 and V2, and so both the dot products are 0. So we take the whole equation for the line, R1 and R2, and we imagine subtracting them. And for any s and any t, this gives you a line segment between the point R1 and the point R2. And that line segment at closest approach is perpendicular to both V1 and V2. And so at closest approach, these 2 equations are both true. R1 minus R2 dot V1 is 0, and R1 minus R2 dot V2 is 0. So what is this R1 minus R2 object? Well, you can simply subtract the vector representation of both line segments, and you get negative 1 plus 3t minus s, 2 plus 2t minus s, 4 plus 3t. You get an expression containing both t and s. And then you take the dot products with v1 and v2, and you get two equations for the two unknowns, s and t. And it's a little bit messy, so here's the dot product number 1, and here's the dot product number 2. You get sort of all these terms, and that has to equal 0, and all these other terms have to be equal 0. And then you're sort of simplifying. You simplify the equations down a little bit. It's really not clear to me. You simplify the equations down here, and then I'm doing a little bit of, doing a few steps in my head here. I'm taking 2 times this equation minus 5 times this equation, which cancels out the s's. All right, and so 2 times the first equation minus 5 times the second equation gives me this equation, which s is missing. And then similarly, here I want to get rid of t, and it looks like I've done 22 times the bottom equation and 5 times the top equation. And you get this equation when you subtract those, where the t's are missing. So now I have an equation for t, an equation for s. I solve for t, I solve for s. It's messy. Real life is often messy. I've got these fractions, weird numerators and weird denominators. If you feel confident that you've done a problem correctly and you get strange numerators and denominators, just keep going. Let go of this idea that you'll never encounter weird numbers in the textbook, and certainly let go of the idea that you'll never encounter weird numbers in real life. So we get here these numbers. We then plug these numbers back into our line segment here. For this displacement vector, r1 minus r2, this is then the displacement between those 2 points that are closest together, and we take its magnitude and we get another number. Again, sorry that I did too many things in my head there, and this is a more complicated example maybe than was appropriate for a first video on the subject. This is definitely advanced material, and if you understand all the rest of the examples, then you're in pretty decent shape and ready to come to class.